Hello, I'm Evgenios and I will present to you our latest leakage abuse attacks on encrypted databases. This is a joint work with Babis Papamanthu from the University of Maryland and Roberto Tamasia from Brown University. In the setup of outsourced computation for databases, we have a client depicted on the left and a server depicted on the right. At setup time, the client uploads the records of the database to the server and later on issues a query for which the server responds with the records that correspond to the query. Of course, this is the plain search with no security whatsoever. The area of encrypted search addresses the same task, but with the additional requirement that the server should not learn valuable information about either the query or the responses. Therefore, the query is encrypted, an encrypted index is used to retrieve the answer, and the response is encrypted as well. The area of searchable encryption, or more generally structured encryption, has evolved a lot during its conception in 2000 by the work of Song, Wagner, and Perig. We now have works that handle expressive queries, works that focus on the efficiency and the scalability of the cryptographic constructions, as well as works that derive lower bounds on theoretical analysis. One of the reasons that this cryptographic primitive attracted so much attention is its practicality, which unfortunately comes with the cost of revealing some information, the so-called leakage function. This leakage is revealed by construction, and we have cryptographic proofs that show that no other information is revealed but this rigorously formulated leakage function. So let's define the typical leakage in these cryptographic schemes. The adversary is an honest but curious server that observes the token, which is the output of a keyed random function that takes the query as an input. The adversary also observes a set of individually encrypted records that are retrieved during the encrypted query execution. Since we are dealing with a persistent adversary, the server will observe a series of interactions of this type. Let's now see what the adversary can infer from these interactions. The first thing is that the adversary can count how many times the client issued the same query by simply counting the number of times he has seen the same PRF output. In this illustration, the adversary can tell that the token T is issued twice, but he cannot tell what is the underlying plaintext. This is the so-called search pattern leakage. Another inference that the adversary can make is that the same encrypted record was returned in multiple encrypted queries. For instance, in this example, all encrypted queries return the ciphertext of the yellow record. This is the so-called access pattern leakage. With the term leakage abuse attacks, we refer to algorithmic techniques that take as an input the leakage that I just described and output a reconstruction of the underlying plaintext values of the database. So let me give you a brief overview of the state of the art in these attacks for geometric queries. To better illustrate the limitations of previous techniques, I will also explain the underlying assumptions they rely on that concern the query and the data distribution. When it comes to leakage from encrypted k-nearest neighbor queries, the state of the art is the work by Kornaropoulos et al. From S&P 2019 that relies on the uniform query distribution assumption. This means that the attack expects the queries to be chosen uniformly at random from the domain, otherwise the reconstruction is incorrect. Moving on to range queries, the pioneering work by Kellaris et al. From CCS 2016 sets the foundation for all modern leakage abuse attacks that you will see in this slide. Their attack on range queries also relies on the uniformity assumption. La Charité et al. Presented in S&P 2018 an attack on range queries without the uniformity assumption, but their technique crucially relies on the assumption that the database is dense. This means that for every possible value, there exists at least one record with this value. It is unclear whether this density assumption is common in practice though. Then the work by Grubbs et al. From S&P 2019 presents three attacks with different assumptions. Both the generalized KKNO and the approx value crucially rely on the uniformity assumption. The AOR to ADR is a two-step attack. The first step is called AOR, and it reconstructs the approximate order without relying on any density or query distribution assumptions. The second step translates the AOR output to an approximate data reconstruction, and for that, the attacker relies on detailed knowledge of the query and data distribution. The current set of assumptions is not satisfying, which resulted in quotes like the following. While there has been some progress on designing attacks against structural encryption, these attacks remain mostly of theoretical interest due to strong assumptions they rely on. To illustrate what the uniformity assumption really means, I will use an example on the two-dimensional domain. Suppose we could all safely be at the same conference room in downtown San Francisco. Then the uniformity assumption implies that the probability that you issue a query from your phone during the lunch break of the conference is the same as the probability that a query is issued from deep into the water of the bay. In this work, we deliver the state of the uniform address and present the first leakage abuse attacks that are agnostic to the query distribution, and they do not assume any knowledge of the data or query distribution. Our work is the first that reveals the synergy between search pattern and access pattern leakage. The secret for the generality of our algorithms comes from the novel use of non-parametric estimation techniques on the search pattern leakage. It is worth noting that none of the proposed attacks so far utilize the search pattern leakage. Armed with this new insight, we revisit the leakage of range queries and use techniques from statistics and optimization to derive our reconstruction. We also revisit the k-nearest neighbor attacks from S&P 2019 and show how to improve them so as to use less number of queries and scale them to larger values of k-nearest neighbors while removing the assumptions about the query distribution. In this presentation, I will focus on the attacks on range queries. Let's start with the assumptions that we make. We assume that the boundaries of the domain of the plaintext values, alpha and beta, are known to the attacker. We assume that the encrypted database under attack is static. We assume that the client receives the exact response for each query. That is, there are no missing records or additional records. Finally, we assume that the query distribution does not change during the attack and that queries may have arbitrarily small but non-zero probabilities. Also, the queries are independent and identically distributed. Notice that our attacker does not know the underlying query distribution. The question that we pose is, what can the adversary learn from the search pattern leakage? I will illustrate our approach with the following example. On the left-hand side, you see a series of tokens where each of them is the output of a key-to-random function that takes a pair of values as an input for the range. On the right-hand side, you see the corresponding encrypted records that are returned for each of the queries. As a next step, we partition the observed token response pairs into multisets, and each of them contains the tokens that have the same response. The end result looks as follows. We will focus on this set. The next question we ask is, how many distinct tokens exist that return this specific response? Since we are interested in distinct tokens, we can remove the multiplicity from the multiset and count the remaining unique tokens. At this point, the attacker can say with certainty that there exist at least 3 tokens that return this response, but unfortunately, he doesn't know with certainty how many tokens have not been observed. But let's take a step back and think why this question is important. In order for the response to be v1, v2, v3, the range query that the client issues must have a lower boundary anywhere in between v0 and v1, and an upper boundary anywhere in between v3 and v4. Therefore, the number of distinct range queries with response v1, v2, v3 is equal to the product of distances between plaintext values. Notice that if the attacker infers the pairwise distances between plaintext values, then he can reconstruct the plaintext database by stitching the distances of consecutive values. Since we cannot know with certainty the total number of tokens that return a fixed response, we turn to the next natural question. Can we estimate the number of unobserved tokens that give a specific response? To be more rigorous, we denote by T the random variable that takes values from the universe of tokens, and by R the random variable that takes values from the universe of responses. Then the multiset of observed tokens for a specific response can be seen as a sample from a conditional probability distribution. Since the total number of tokens corresponds to the support size of the conditional distribution, we can proceed as follows. We first count the frequency of each observed token and create a multiset of frequencies. Using this information as an input, we can deploy a support size estimator to derive an estimation about the product of distances between plaintext values. I'm not going to give any details on these estimation techniques, but I would like to point out that we tested two approaches, namely the jackknife estimator and the variant-variant estimator. Both of them are non-parametric, which means that they do not need any information about the underlying probability distribution, and they both take as an input just the frequency of each observed token. The inner workings differ since the jackknife deploys a bias reduction technique, while the variant-variant constructs the simplest histogram that explains the observed frequencies. Therefore, the answer to the previous question is that the adversary can estimate the product of pairwise distances from the search pattern leakage. Even though that is a big step forward, we are not there yet, since we only infer the product of two distances and not each distance individually. I will now give a brief overview of the entire attack algorithm. Suppose we have only two plaintext values, v0 and v1, and their location is unknown to the adversary. We will switch notation and refer to the pairwise distance between values with a capital letter L for length. Then by L0, we denote the distance from the beginning of the domain to value v0, by L1, the distance from v0 to v1, and by L2, the distance from v1 to the end of the domain. We switch now to our honest but curious attacker. The first step of our attack is to partition the tokens and analyze each partition as a conditional probability distribution. We use the frequencies from each sample of tokens and derive an estimation about the product of lengths. If the estimation is accurate, then the attacker infers that the product of length L0 and L1 is 350, the product of L1 and L2 is 1015, and so forth. The next step is to derive individual lengths that agree as much as possible to the estimated products. To achieve this, we formulate a constraint minimization problem that uses the lengths as unknowns. The objective function is the sum of squared differences between a product of unknown lengths and their estimated product, which comes from the previous step. For the constraints, we require the sum of lengths to be equal to the size of the universe of the domain. We also require that all lengths must be positive. In our work, we saw that each squared difference can be seen as an equation that requires the product of unknowns to be equal to a number. Therefore, if we take the logarithm of this equality, we can transform each squared difference to be the sum of unknowns as opposed to the product of unknowns. Therefore, we saw how to reduce this transformed objective to a system of linear equations. One more technical detail that I would like to point out is that some support size estimations were made with more samples than others. To account for this phenomenon, we put a weight on each squared difference so as to indicate that some terms are more important than others, since we have higher confidence about the quality of their estimation. I will conclude this talk by presenting some experimental results. In the first experiment, we compare our approach indicated with the orange color here to the state-of-the-art attack from Grubbs et al., which is indicated in blue. On the y-axis, you see the mean squared error, so the smaller the error, the better the reconstruction of the attack algorithm. On the x-axis, you see the density of the database that ranges from 10% to 90% of occupied values. As you can see, our technique outperforms the state-of-the-art, which is remarkable because our attack does not know anything about the query distribution, while the generalized KKNO attack knows that the query distribution is uniform. Therefore, even though our attack is at a disadvantage, it still performs better because it utilizes the search pattern leakage. In this experiment, we switch gears and mount the attack on a query distribution that is skewed towards short ranges. Here you see three heat maps where the y-axis corresponds to the choice of the lower boundary of the range, while the x-axis corresponds to the upper boundary of the range. Each colored square of the heat map corresponds to a distinct range query, and its color corresponds to the probability that this range is asked. The brighter the color, the larger the probability. As you can see, the probability mass of the rightmost query distribution is concentrated around the diagonal, which means that the issued queries are mostly of really short range. As we move towards the left, the distributions allocate some probability mass to larger ranges. This family of query distributions cannot be handled successfully by any of the previous approaches, therefore we cannot compare our performance with the competition. This plot shows the reconstruction error of our attack on the y-axis, and on the x-axis the database density. As you can see, our attack performs really well on concentrated short-range queries that are depicted in green here. This may sound counterintuitive at first, so let me explain. The reason behind this behavior is that since the vast majority of queries are short, we only get a sample from a linear number of conditional probability distribution in the estimation step. Therefore, even though we only use a linear number of estimations among the quadratic number of all possible, the result of each estimation is much more accurate, which translates in a smaller overall error. Overall, our latest work on leakage abuse attack proposes the first algorithmic techniques that use both the search pattern and the access pattern leakage, and are the first to overcome the previous strong assumptions about the adversary's knowledge. Thank you.